Problem number 21. An object launched vertically upward from the ground with a speed 50 meters per second bounces off of the ground on the return trip with the coefficient of restitution given by CR equal 0.9, meaning that immediately after a bounce the upward speed is 90% of the previous downward speed. The ball continues to bounce like this. What is the total amount of time between when the ball is launched and when it finally comes to a rest? Assume the collision time is 0. The bounce is instantaneous. Treat the problem as ideally classical and ignore any quantum effects that might happen for very small bounces. Solution. First, we can write an expression for time of flight. Each time after bounce, time flight is equal to 2v over g, where n is number of collisions. And to find what is the total time, we need to summarize all of this time tn. But each time when we have bouncing, we have Vn equal Cr multiplied by previous speed. And that's equal to Cr power n multiplied by V0, initial speed 50 meters per second. Now we can put this to expression and find that Tn equal 2V0 over G multiplied by Cr power n. And total time will be this sum from n equals 0 to infinity. And after all, we have sum of geometric progression, which has this form. And the final result is 100 seconds. Problem number 22. A solid ball is released from rest down inclines of various inclination angles theta, but through a fixed vertical height h. The coefficient of static and kinetic friction are both equal to mu. Which of the following graphs best represents the total kinetic energy of the ball at the bottom of the incline as a function of the angle of the incline? Solution. Here we can find that initially when angles are very small, less than critical, it means that tangent theta less than coefficient of friction, our ball is moving without sliding and we are not losing kinetic energy. It means that only C, D and E could be solutions for this case, not A and B, because they start to lose kinetic energy from the beginning angles. Later, when angle increasing almost to 90 degrees, we have very small friction and we are not losing energy at all when angle going to 90 degrees. It means that only C and D could be possible solutions, not E. And finally, we can tell that this graph must have a continuous function, because initially when we just reached the critical angle tangent theta equal mu, we are losing just a slight energy, and if we increase this angle, this loss of energy will increase. And after when we reach the minimum, a loss of energy start to decrease and finally it's going to 0. It means that here we are not losing energy. But on graph D, we start to lose a lot of energy just after critical angle, which is not true. So most possible diagram is C. I would say this diagram is not firmly good enough, because this behavior of function, it has no gap for the first derivative of this function. So it means that this graph represents not very correct answer, but still it's a best choice, C. Problem number 23. A 2 kg object falls from rest, a distance 5 meters, onto a 6 kg object that is supported by a vertical massless spring with a spring constant K equals 72 newtons per meter. The two objects stick together after the collision, which results in the mass spring system oscillating. What is the maximum magnitude of the displacement of the 6 kg object from its original location before it is struck by the falling object? Solution. Here we have several steps to solve this problem. First step, we have to find what is the speed of the first object of 2 kg when it reached the second object. Here we use energy conservation. To find this speed, V0, we use this formula, V0 square equal 2gh, or 100, and the speed equal 10 meters per second. Second step is to find what is the common speed of both objects when they stick together. Here we use momentum conservation. From momentum conservation we can find that the common speed of these two objects, v1 equals m1 over m1 plus m2 multiplied by v0, which is 2.5 meters per second. Next step, we can use energy conservation. So we have kinetic energy of two objects, which we can count, and it's turning to potential energy of these objects in the lowest point when they stop. So their kinetic energy equals 1/2 m1 plus m2 multiplied by v1 square, which is 25 joules. Last step, we can use energy conservation. For that we have to find the initial compression for spring, which will give us initial potential energy of spring. X initial equal m2g over k. And now we can write the energy conservation. We have a final potential energy for spring equal 1/2 kx plus xi square. That's equal to potential energy of these two masses, gravitational potential energy, plus initial potential energy of spring, plus kinetic energy. After all, it will give us this quadratic equation. When we put numbers, we have this quadratic equation. We have two roots. One is positive, which represent the lowest position, and the negative represent the highest position. And by magnitude, lowest position will be greater than highest position. So this is why we have for answer positive root, and that's equal about 1.15, which is B answer.